We're going to be learning about symmetry. We're also going to be learning about some transformations, but we're going to be starting with symmetry, okay? You guys have probably heard that word before. What do you think of when you hear the word symmetry? Symmetrical, but what does it mean to be symmetrical? What does it mean to be symmetrical? Equal on both sides, okay? All right, so typically when you guys think of the word symmetry, you maybe think of, like when you think of objects that are symmetrical, maybe you think of like a butterfly, right? If we folded like a butterfly in half, the wings have like the same pattern, right? It matches up, right? When the butterfly, when you look at its wings, okay? So that type of symmetry is a specific type of symmetry called line symmetry, okay? So line symmetry is going to be your first definition, okay? Line symmetry is the kind of symmetry like a butterfly's wings. And I think it's the most typical, like it's typically what we think of when we hear the word symmetry. Okay, here's the math definition for it. It is a property of a figure in which after a reflection the figure maps onto itself. Okay, so it's saying when we do a reflection that the figure is matching up with itself completely. Okay, if I drew a line and I reflect one side of the figure, then it matches up with the other side perfectly. Okay, so let's take a look at some of these shapes. Does this shape here, this rectangle, does it have any lines of symmetry? Is there a way that I could like fold it and it would fold perfectly on top of itself? Yep. Where could I fold it? Up and down. So if I drew a line up and down, I can make a fold right there and this side would match up onto that side, right? So that's a line of symmetry. Draw that line onto your paper. Okay, where's there another line of symmetry? Across, like horizontally? Yep. Okay, so there's another line. Are there any other lines of symmetry? Okay, so the last class also thought maybe it had a diagonal line of symmetry, so I'm going to kind of show you with this trace paper. If I fold it diagonally, look what happens. Does it actually end up on itself? No, okay? You can see that this corner over here doesn't match up, so it doesn't have any symmetry diagonally, okay? There's no line of symmetry there. So this one actually just has two lines of symmetry, okay? Two lines. All right, let's take a look at the next figure. You guys think that one has any lines of symmetry? You think one? Where do you think it is? I heard someone say one. Where do you think that line of symmetry is if it has one? Catherine? Like through here? Yeah, okay, so let's take a look at that. I traced the triangle with trace paper, and I'm going to fold this trace paper and see if it actually matches up. So does it actually land on itself? Yeah, right? Does that make sense? So there's actually a line of symmetry kind of cutting this just like that, right? Okay, so are there any other lines of symmetry for this triangle? Like if I go this way or that way, is that going to make? No. Okay, so this one just has the one. All right, what about for the next one? Does anyone think they see something? No. Catherine, what do you think? Like if I folded it on the corner? Okay, so let's take a look. So if I trace this image and I then fold it on the corner, does it end up laying or mapping right onto itself? Yeah, okay. So there's a line of symmetry here in the corner. Okay, now, any other lines of symmetry for this shape? Like if I fold it this way or I fold it that way, is that going to make a line of symmetry? No. Okay, so just the one. All right. Okay, questions there? No questions? Okay. All right, let's talk about our next type of symmetry, which is rotational symmetry. Now, this is the type of symmetry that people don't typically think of when we say the word symmetry. Okay? But it is just a different type of symmetry than line symmetry. Okay? So rotational symmetry is when we can, like, what do you guys know about rotations? What does that mean? Yeah, spins, like it goes around like in a circle, okay? So if something has rotational symmetry, that means when I spin it, I can spin it and it lands like perfectly on top of itself, okay? So here's the math kind of definition. Okay, so it's a property of a figure in which after a rotation, the figure maps onto itself. Okay, so let's take a look at these figures down here and check and see if they have any rotational symmetry, okay? So I traced over this square. I put a little mark at the top just so that I would know like when I'm rotating it when we're back to where we started, okay? So if I'm going to rotate something, I'm going to rotate it around a fixed point. So let's say the point is in the middle of the square and I'm rotating about that point. If I rotate that much, then the square is right back on top of itself, right? So I've done one turn, okay? Okay, there's another turn. So how many total turns? 2. Okay, I turned it a third time. Now it's on itself again, right? And now, can I still rotate it again? Yeah, 4 turns to get back to where I started, right? Like 1, 2, 3, 4, right? Okay, so this thing, because I can turn it and get it to lay on top of itself, that does have rotational symmetry, okay? Now, it's talking here about the angles of rotational symmetry. So, how do I know what the angles of rotation are? Well, here's what I do. How many total degrees in a circle? 360. So I take the total degrees in a circle and I divide it by how many turns it took me to get back to where I started. So how many did it take me? 4. So what is 360 divided by 4? If you guys need to, use your calculator. What do you get? 90, okay? So 90 is my first angle of rotation that I have symmetry at. Okay, now, how do I find all the other angles? Well, I take 90 and I add 90 to it again, because 90 is telling me how much each turn is, so the next one would be at 180, and then add 90 again. What do I get? 270. Now, what happens if I add 90 again? I get to 360, which means I've gone a full circle, right? I don't include 360 in my angles of rotation. Here's why. If I take any object and I rotate it a full 360 degrees, doesn't it get back to where it started? So every object has rotational symmetry at 360 degrees. I'm concerned about all the other angles less than 360. Does that make sense? So I don't count 360, okay? All right, so let's take a look at this one. If I rotate this triangle, okay, is it ever laying back on top of itself? I mean, it's parts of it, but is it completely 100% perfectly back on top of itself? Now it is, but how much did I have to go to do that? I had to go a full circle, right? So does this one have any angles of rotation less than 360? No, so write none. Okay. All right, so let's take a look at the arrow. Okay, so if I'm going to rotate this arrow, is it now on top of itself? Okay, so I've done one turn, you could say. I'm going to rotate it again. And now that's 2 turns to get back to normal, right? So I find the angles of rotational symmetry by doing 360 divided by how many turns did it take me to get back? 2. So what does that equal? 180. Okay, so my first angle of rotation is 180 degrees. Now, what happens if I add 180 to itself? I get 360. Does 360 count? No. So I just write down the 1. Okay? Does that make sense there? All right. Okay, so let's take a look at these last examples. Okay? What it's asking us to do is it wants us to describe the type of symmetry for each figure, then draw the lines of symmetry and name the angles of rotation if there's any, okay? So let's look at this figure here. Okay, this figure, it's like a pentagon, but it has these little spikes coming off of it. Do you guys see those little spikes? Okay, those are part of the figure, all right? So if it's going to have some line symmetry, it kind of looks like maybe if I fold it down the middle. But look what happens when I fold it down the middle. Does this spike line up with the one that's down here? No, it's up here, right? So is this perfectly symmetrical with line symmetry? No. Okay, and I could keep trying this, like different folds, and I'm going to get those little spikes just won't match up. Okay, so does it have line symmetry? No, so we're going to write none. Okay. All right, now, what about rotational symmetry? Okay, so I drew a dot up here so that I would know like when this point gets back to where I started. But let's take a look at turning it. Okay, there's one turn. Is it now on top of itself? Yeah, okay. 2 turns. 3. Right? 4. And how many to get back to where I started? 5, right? Okay. So, how am I going to find the angles of rotation? Divide 360 by 5. So, what's your first angle of rotation? 72? Okay, now to find all the other angles, I keep adding 72. So 144, then add 72 again, 216, 288, okay, back to 360. So I don't need to list that one. Does that make sense? Okay, so what type of symmetry does this figure have? Rotational. All right. Okay, I'm going to give you guys a moment really quickly to discuss number 5 with the people around you. See if you can figure out whether it has line or rotational symmetry. If it has rotational symmetry, list the angles of rotation. If it has line symmetry, draw the lines of symmetry. Okay? Try that one. All right, so let's take a look, okay, at what you guys should have come up with. Okay, did it have line or rotational? Line. The line was one line through horizontally through the middle here. Okay, there was not, rotational didn't work, right? If you tried to turn it, it didn't come all the way back on top of itself until it got back to 360 degrees, right? Like if I move this point of the arrow, it would be down here, then over here, then up here, but then it would finally end up after 360, okay? There's only one line. No matter if I drew diagonal or up and down or another diagonal, it wasn't going to flip, like reflect onto itself, okay? Are there questions?